Okay, so let me continue to talk about how we get the accelerations from this equation. So right now this is the same sketch, and then the uh, green colored writing represent the relative velocity and relative position. Okay, so means everything is defined in a local rotating frame. So right now the VBA is A dot I plus B dot J, and this is position AI and BJ. So this small character IJ is a unit vector of local rotating frame. And then just remember that the time derivatives of the unit vector of rotating frame is omega cross product I and omega cross product J. Okay, so these are kind of starting position. So let's do the acceleration. So acceleration is time derivatives of your position vector, right? So let's take a time derivatives of this one. So if you take a time derivatives of your position B, that becomes your acceleration, right? And this one also. So if you take a time derivatives of this one, this becomes acceleration as well. And then I want to take a time derivatives of the relative one, okay? And plus, we need to do that one. So this is omega dot cross product RBA, and plus omega, and the dot means the derivatives, and then I just write down as a dot, okay? So this, let me just change this one as a dot, because let me just use the dot notations for derivative, okay? So when I just take a time derivatives, I can write down in this way. And let me just write down, keep writing down this one. And this is and the time derivatives of omega will be alpha, the angular acceleration of the rotating frame. Okay, so this is alpha and R, B, A, and this one so what is this one? So this one is the derivatives of all this one. So if I just write down AI and BJ and DT. But the last time we kind of know that if you take a time derivatives of this one, it becomes this one plus omega INR PA. And how about this one? So let's just think about that one. Before we proceed this one, let's just think about this one first. And here, okay, I want to figure out what's the time derivatives of the relative velocity. Then relative velocity, so let me write down in this way. So I want to do this one, right? So your velocity, relative velocity is A dot I plus B dot J. So I want to take a time differentiation of A dot I plus B dot J. So if I just do that differentiations, the first one becomes A2 dot and I, and A dot I dot, and PB2 dot J, and B dot J dot, right? So A2 dot I plus be 2 dot j, and plus we know that this I dot and j dot can be replaced by this omega cross product I and omega cross product j. So we can write this one like omega cross product and A dot I and B dot j. Okay? Then what is this one? So I2 dot B dot 2 dot. So that's the acceleration, but this is acceleration defined in local frame. So I can say A, B with respect to A. Okay? And this is omega cross product. What is this one? This is the velocity. Okay? So let's substitute this one with this one. Okay? So let me substitute this one. So if I just substitute this one, this is A, and this is the acceleration of B with respect to A, and plus omega and B, A, and plus alpha R B A, plus omega cross product this one. So then this is a little bit long, so let me just rewrite this one here. So this is A, O, A, B, B, O, and then omega cross product VBA is here 2. So we have 2 omega cross product VBA, okay, and then alpha and RBA. And then we have another term, omega times, not the times, cross product, and omega cross product RB. So, let's look at this one. So, from here to here, okay. So this is the this is the acceleration term, okay. So maybe I can say so the last two terms kind of represent the motion of a rotating frame observed from the fixed frame. So this is the tangential component, so alpha r is a tangential component of acceleration, and this is normal component of acceleration of B with respect to A. Okay? And then this is the acceleration of origin of local frame if there is any accelerations, and this is the acceleration of B with respect to A. Okay. So right now, this is also defined in the local frame, and this is all defined in the local frame. Okay, and this is also defined in the local frame. And then if you just look at this one, let's say everything is rotating with omega and alpha. Okay. So if this rotating frame is kind of accelerated, so in order to get the acceleration of B with respect to O. Finally, this is A, B, O. We need to take the acceleration of origin A into our consideration, which is this one. And then for the acceleration, so right now we need to also add the acceleration of B with respect to A, just as we did in this kind of velocity as well, because when you get the velocity of B points, we consider the velocity of A point, and plus we just consider the velocity of B with respect to A. Likewise, when you try to get the acceleration of B, we consider that acceleration of origin of local frame, and also we consider the acceleration of B with respect to A. And then this one is rotating with certain accelerations. And then the last two terms, okay, is the tangential acceleration and normal accelerations at that instance, okay. And then finally we have a little bit weird term, which is this one, okay. This is called the Coriolis acceleration. So the Coriolis acceleration actually is not actually present. Okay, so sometimes people say the Coriolis acceleration, Coriolis effect is a fictitious effect, because this is kind of invented term to express or represent or explain certain motions, because you observe the motion on the rotating frame. That's why we have to add this kind of Coriolis acceleration term. So in this lecture, let me just explain what's the meaning of the Coriolis acceleration. Let me just erase everything except this one. Okay, so let me just erase all my process here. Just leave it here. Okay, so finally we have this equation and this equation. Then what is a Coriolis acceleration? It's very simple meaning here. So just imagine, okay? Just imagine that like we have a cylinder, and this is and cylinder is kind of rotating, okay? And then we have a gun here, okay? So this is like a cone. And then this is marker or aiming, okay? So if you just aim this one and just fire the gun, okay, then this bullet is kind of moving, okay? But what happened? Because this kind of cylinder is rotating, okay? So sometime later, this kind of rotating, so if I just draw back, if I draw again, your kind of marker or aiming thing is kind of rotated about this much, because this is rotating. So about the time when the bullet reach to this position, your kind of marker is already kind of deviated, because this one is rotated. Okay, it's very simple to understand this one. Okay, then what if you kind of stand there? Let's say you just sit there, and then you observed the motion of the bullet from your position. Okay? So your body also rotates with the cylinder at the same time. So your body is sitting here, but you don't know whether or whether your body is rotating with the same cylinder or not. So if I drew exactly same thing, so this is cylinder, so exactly the same one, but you're standing there. But if you just observe the bullet motions from your position, the bullet looks like deviated, isn't it? Because actually the bullet has not been deviated actually, because the bullet just moved through just with a linear straight line motion, but your cylinder is kind of rotated. But if you observe your bullet from your position, because your cylinder on which you're standing is kind of rotated, that's why bullet looks like a deviated from you. Okay? So in order to explain those kind of deviations, we need to invent another kind of fictitious force. Some force is kind of acting this bullet, that's why the bullet is kind of deviated. So that is Coriolis effect. That is Coriolis effect. And then the kind of the force term or acceleration term that explain those kind of deviation is this Coriolis acceleration. So so let me give you another kind of example. So this is the Earth, okay? Let's say this is Earth. And from the North Pole, let's say you launch missile, okay? You launch a missile, and this one is going there. But you are standing on the globe, so your globe is rotating. So basically, if you observe the kind of motion of the missile is kind of deviated from you. So this one looks like going in this way because you're kind of rotating. So there might be some kind of force that push to the side. Okay, that force can be explained by this kind of Coriolis acceleration term. So this is mass times acceleration, which is 2 omega and the v of your missile. Okay, so this is omega, the global acceleration, angular velocity, and this is the velocity of missile. Okay, so what's the direction of this one? The direction will be the negative, because this is omega is top, and this is velocity is going this way. So if you just use the right hand rule, the direction of this one will be, so we need to put the negative here to accelerate on the left side. Then I can give you another example here rather than the close one. How about this one? So just erase this one. So we have a frame, okay, and then this one is kind of rotating, and then we have a fixed frame. Okay, So this is our fixed frame, and this is kind of rotating. And then let's say you just throw the ball. The ball is kind of moving past through this kind of rotating frame. Then if you just look at the motion of the ball from the top, so let me just use this one, and the ball is coming this way, okay. Sometime later this one is rotating, okay, but the ball is still going this way, okay. Sometime later the ball still just keep straight. But if you observe the ball on top of your rotating frame, so you are still there. So right now you're sitting inside, so this is outside. Your ball is moving this way, but after this one is rotating, you are still in the same frame, but this one looks like that. Okay. Because you're kind of rotating, that's why ball, even though the ball actually move move the straight line, when you look up the ball, because this one is rotated, the ball looks like deviated. Okay. So let me just explain this kind of phenomena using our expression, using this equation. Okay. So the ball is kind of keep moving it without any acceleration, with a certain constant speed. Then your ball's acceleration will be 0. Okay. And then right now your local frame here is rotating with the same axis. That's why your velocity, let's say this is A, so velocity of A will be 0. And this is the accelerations with respect to your frame. So we want to get that acceleration. And then this is 2 omega and this one. And then right now, let's say this one doesn't have any acceleration, angular accelerations. So this term will be 0. Okay. And then we still have this one. So if use the scalar term, and this one can be minus r, like that. So what is the acceleration of your ball with respect to your position A? So from here we can get A, B over A is equal to minus 2 omega and plus so finally you have this term. So this is the acceleration of the ball with respect to your position A, which is rotating frame, is minus 2 omega cross product the VBA. So actually the ball kind of moving in this way, and this is the center. So what's the direction of this one? So the direction of the Coriolis term, whenever this one is ball moving, it's kind of perpendicular to the ball motion. Okay, so this is 2 omega and r v. And also we have one other term. This is centripetal term. So this is RVA v square. So basically the centripetal is this direction and this direction. So when the ball kind of move, the ball has a centripetal kind of force, which is the outside, and this is Coriolis effect. This is perpendicular to the motion of the ball. That's why the ball is kind of deviated because of those kind of acceleration terms. they're kind of pushing down, that's why the ball is kind of deviated. So from your position, which is local A, we can express the motion using this Coriolis term and centripetal term. Okay, so I hope you can kind of understand this part here. And then I kind of explain all the theory underlying those kind of relative motion analysis using rotating axis, especially for the velocity and accelerations. And then please review this kind of boring lectures. And then the important thing is that you need to look up the examples from your textbook and just understand how the example utilize those kind of equations into the actual problem sets.